Hey again. Let's talk about the gamma distribution and talk about how useful it is and talk about how it's kind of a boss distribution in the sense that a lot of the ones that we use every day are actually special cases of it. So let's take a look. So here's lambda to the r of the gamma function. So that's gamma r times x to the r minus 1 times e to the minus lambda x. And that's for x greater than 0, r greater than 0, and lambda greater than 0. Okay, so if we were doing that little trick that we did when we were thinking about is everything greater than, is f of x such that it's greater than or equal to 0? Yeah, because all the pieces in it have to be greater than or equal to 0, then that would be true. Okay? So, anyhow, when we have certain restrictions, for instance, the exponential is a special case, the chi-square, which we'll talk about in some detail soon, is a special case, and so on. So what we try to do a lot when we're finding expected value of several distributions is set it up such that we have a gamma underneath the integral sign, because we know if we've got a probability function under the integral, it's going to go to 1. Pretty good. Okay? And then we don't have to do any real elaborate integration. All right. That being said, let's take a look at the exponential. This is what we did in the handout, but I thought I would just go through it again. Sometimes it makes better sense. And I know I went through it, but now that you've had a chance to go through some of those extra ones, and I know a lot of people were out that first day because of the rain, so we can sing that song, Blame It on the Rain, like Milli Vanilli. You guys probably don't even know who they are. Okay. Anyhow, they used to lip sync. So let's look at the exponential. So the exponential distribution is just plain old f of x is lambda e to the minus lambda x, and that's x greater than 0, lambda greater than 0. Okay, and I want to find the expected value. Fair enough. So, and again, if we talk about what we said in the previous movie, if I just say the expected value, that just means e of x. Okay? Unless I put some kind of conditioning on, as I did in the previous movie when we had that e of x cubed. All right, but if I just say the expected value, that implies e of x. So that means I'm going to have the integral going from 0 to positive infinity of x times lambda e to the minus lambda x dx. All right. And because I'm sneaky and I like doing things like this, I'm going to take that lambda, it's a constant, and I'm going to push it on the outside. I don't trust constants. They're up to no good. So that's on the outside. I have the integral of x e to the minus lambda x dx. Okay. So I look at this and I say to myself, what if I put a 1 on there? I mean, because it really is there. We just don't think about it, okay? And that makes me think a little bit about the gamma distribution, because when I have the gamma, isn't that to the r, I have the, on the x, I've got that power r minus 1. So just pretend for a second, and don't worry about the the lambdas and the gammas right now. Let's just pretend that this is a gamma. Okay? So if this were a gamma, and I know if I flip back a couple of pages, and I can't do it on here, it won't let me, the power on the x is r minus 1. So if r minus 1 is equal to 1, then what must r be equal to? Right, good. 2. Okay, so hang on to that thought while I change pages. Okay, and I'm going to put the gamma back up quickly and small. So that's, oops, r gamma r x to the r minus 1 e to the minus lambda x. Sorry, the x is up there. Okay, so let's look at what we have. Here's the gamma up here. Okay, so what we have right now is lambda sticking out there, and I have x to the first e to the minus lambda x dx. Everybody happy so far? Okay, so I know, again, this is the definition of the gamma right here. This is the definition. I also know when I look at these terms in the front, those leading terms, those are just constants. They don't have the x's in them or anything. So if I multiply them back in here, right in here, I can divide on the outside of the integral and nothing bad will happen. It's just like if I multiplied a 4 here and if I multiplied by 1/4 over here, nothing bad would happen. As long as I don't multiply by x's, I'm okay. All right? So we already know that r is 2. All right? So what if I say, okay, let's put in lambda squared, because it's lambda to the r, over gamma function of 2. We'll talk about gamma function in a second. So if I multiply it like that, then I've got to divide by that, or essentially invert and multiply. So I have my gamma of 2 times, okay, and there's your lambda sitting out there minding his business. Okay, and this is still expected value of x. Okay? All right, now let me change colors for a second. All this stuff in the red square brackets, isn't it true that that is the definition of a gamma function such that r is equal to 2? Yes, it is. All right, so that is a gamma probability function, a probability density. All right, now I'm going to integrate. Sorry, I forgot to put my limits of integration. If I integrate across a probability function, what do I get? Right, 1. So I have lambda times gamma of 2 over lambda squared times 1. Wow, pretty cool, huh? All right, what's going to happen? Cancel this baby. Get that one down. What do I know about my gamma function? Well, I know that when the term in the parens is an integer, let me write over here, that when when r is an integer, then my answer is r minus 1 factorial. So I have 2 in there, so I have 2 minus 1 factorial. I still have that over lambda. I'm multiplying by 1. But 1 factorial, of course, is just 1. And I have 1 over lambda, which is as it should be. Okay? And that's how you do it. And this is really a pretty standard kind of way to do things in statistics. What you do is try to fix things up so you do get a probability distribution under the integral. So it goes to 1, and then you just have some constants to mess with on the left, and you've got it. Okay? Hope that helps.